So our next speaker is Jarrett Johnson, and he'll be talking about POP3 galaxies and what they do.
Right, thanks. So it's great to be back at First Stars and to have the chance to present research I've been involved with studying the brightest primordial galaxies and accreting black holes, the two sources that might be the brightest primordial objects in the early universe. The work I'm going to present has been done in collaboration with a number of people who are shown here on the main publications I'll cover. And let me just start by echoing what we've heard already in terms of reviews of population 3 star formation and the evolution of the very first galaxies. I think it's true that we do have a fairly sound understanding of how the physics works in the early universe, starting from the Big Bang and the processes that cool the gas and allow the formation of those first objects. I've taken this still from one of the first billion years calculations made by Claudio Della Vecchia. You can see one of these early galaxies in a simulation volume where you can see actually supernova bubbles being blown out here, the first stars in the middle of these objects producing high energy photons that are transforming the universe. And we can make predictions based on these detailed calculations, right, for what we expect the first objects to look like. And those predictions, as we've also heard, are going to soon be tested fairly closely and scrutinized by future missions like the James Webb Space Telescope, which is going to be launched, as we've heard, in 2018, and if we're lucky, first data in 2019. And by the time we're back here at First Stars 6, or back wherever First Star 6 is, I suppose, we may all be poring over data from this mission, and we'll have a lot more to say. But that's not the only thing. Of course, on the European side, the Extremely Large Telescope is another example of an instrument that's going to be coming online soon, a few years after the James Webb Space Telescope is the current schedule. And this will be the first 40-meter class telescope that's, again, optimized in the optical infrared for looking back at the earliest galaxies. So one question that comes up when you're standing on the verge of all these new observations is, and the search being on for the very first primordial objects, is what should we expect them to look like? What kind of smoking gun signatures can we hope to find so that we know when we've found the first galaxies, the first stars? So we heard in, for instance, Sylvia's review yesterday that one of the generic predictions for primordial stars is that their low opacity probably leads to the envelopes in those stars being fairly limited in extent, which means that at a given luminosity, their temperatures are relatively high, which in turn means that you expect them to be fairly strong UV sources, strong ionizing sources as well, and to have hard UV spectra in particular. So that, in combination with the fact that you might expect the population 3 IMF to be fairly top-heavy, leads you immediately to predict that the nebular emission that's powered by those objects should be really fairly intense. And not only in Lyman alpha, for instance, from ionized hydrogen, but also from doubly ionized helium. So 1640 angstrom emission has been predicted for some time. You can see the citations here going back a number of years to be one of the signposts of primordial star formation. What I show here is actually a calculation of the emission you'd expect from a prompt population 3 starburst in the early universe that I carried out with Volker Braun and his group in Austin a number of years ago. You can see the cosmological simulation here, the sort of the profile of the H alpha emission there. On the left side, this is the plot of the ratio of the 1640 line to H alpha as a function of the time of formation of that primordial stellar population. And these lines vary to some degree due to the sort of mechanical feedback that the hard ionizing radiation has in the gas. So as we've already heard in the last talk and a couple of others, there's this really intriguing object CR7, which is actually a really nice test bed for us to study when thinking about what the first galaxies might look like. And it is a bit of a head scratcher, and there's evidence that we just heard actually that is really valuable in terms of interpreting this object. When it was announced last year, it was the most luminous Lyman alpha emitter above redshift 6. Despite that high luminosity at the time, and I think it's still true, although this is, of course, coming under scrutiny itself, there are no metal lines that were specifically detected, so it was consistent at that point with being a primordial object. And thirdly, and intriguingly, it has this sort of smoking gun signature bright helium-2 1640 angstrom emission, which is suggestive, again, of a primordial stellar population. And in the HST image here, you can see the three components that compose CR7. A is, of course, that bright Lyman alpha and helium-21640 emitting region. And then there are these two accompanying regions, or gas clumps, or more evolved stellar populations labeled B and C. And those come into play, actually, in the scenario for its formation, as I'll come to shortly. And then again, this is the composite spectrum showing that a primordial stellar population can explain potentially that emission. So the two possibilities for what might be powering this object, assuming that it really is primordial and it's not metal enriched to the extent that that star formation has been impacted. One possibility is that it's powered by a cluster of population 3 stars. The other possibility is that it's powered by accretion of primordial gas onto a black hole, and the emission is coming from the accretion disk that forms in that process. If it's the first case, population 3 stars, you have to appeal to a very high stellar mass to explain the luminosity from clump A. Something on order of 10 million solar masses or so is required if you appeal to a very top-heavy IMF. And if the IMF is more modest, something like a saltpeter, you'd have to demand something like 1 billion solar masses in population 3 stars, which is truly an extreme sort of situation. You can actually derive some kind of constraint on the star formation rate if that's the case. If you think about the timescales you have for population 3 star formation, that should be limited by the lifetime of population 3 stars, or some small multiple thereof, because once the most massive stars in their lives, they explode as supernovae, emit heavy elements into their surroundings, and that should shut off population 3 star formation. So you have maybe a few million years to do that. And if you have to assemble 10 million solar masses at least in gas, then you're looking at a star formation rate that's something like 0.1 solar mass per year, or maybe even quite a bit higher than that. So it's a very stringent constraint that would have to be satisfied. On the other hand, if it's an accreting black hole, there are a couple of other constraints that you can immediately derive. The black hole mass probably is higher than about 10 to the 6 solar masses or so, assuming that the emissions from an accretion disk and the models for those match what we typically apply. In addition, the star formation in that object probably does need to be suppressed to some degree in order to not violate the upper limit on the metallicity that's inferred for the object. Although there may be some allowance for some limited amount of star formation, which is an interesting possibility as well. So I'm going to go through both of those sort of scenarios. I'm going to start out talking a bit about the possibility that it's an accreting black hole that powers this object, and then I'll switch back and look at what scenario might have to play out for it to be a population 3 starburst. So this is a plot showing sort of the main two sort of avenues for seed formation in the early universe that we think of for black holes. I'm showing this in the plane of black hole mass as a function of the age of the universe. One of those seed scenarios is population 3 remnants collapsing to become black holes. These would be population 3 stars formed from gas that's cooled by H2 molecules, and you might expect a typical black hole mass of 10 or maybe 100 solar masses for those objects. And then as shown by the arrows here, you can see what happens if they are able to accrete at the Eddington rate, or maybe they experience some intermittent super Eddington accretion if the conditions allow it. The other case is a bit more exotic case, which is what we expect to take place if the primordial gas does not cool efficiently by H2 molecules, but instead has to rely on atomic hydrogen cooling. In that case, you form much more massive black holes. The centers are somewhat more massive halos. The black holes having characteristic mass of about 10 to the 5 solar masses or so. And then those are, for one thing, much more easy to accommodate in terms of explaining the observed quasars powered by the black holes with the highest masses at redshifts of 6 and 7. So the direct collapse scenario actually is really interesting and fits in a sort of a promising way, CR7, for reasons I'll come to, but I just wanted to highlight the fact that the basic ingredients for the scenario are pretty simple. The first one is that you need to have a dark matter halo that's massive enough to bind atomically cooled primordial gas, which cools only down to about a temperature of 10 to the 4 Kelvin after being adiabatically heated during contraction. The second thing you need is some way to suppress H2 molecule formation and suppress the cooling of the gas so that by the time it collapses, it's still relatively hot. And at the center of a halo, such as this that we simulated with Sadek Kofar's group in Munich, what you find at the center of the halo is an object that accretes extremely rapidly on the order of 0.1 or up to 1 solar masses per year. And a number of groups, and I've sort of littered this slide with the citations just to drive home the fact that this is a scenario that's been studied widely at this point, and the main takeaway conclusion is that there appears to be no way to prevent the formation of some kind of supermassive star, quasi-star that collapses into a black hole with maybe 100,000 solar masses or so. I should point out also that there are other conceivable avenues by which you might form this type of object. Invoking some kind of background radiation field to destroy H2 is just the one that's most widely been discussed. So that's actually an interesting point, though, when it comes to CR7. The fact that not only do you have, again, back to this Hubble image of the object, clump A, which may be powered by accretion onto a black hole, but you also have clumps B and C, which are more evolved stellar populations. And when the object was announced, Bhaskar Agarwal and collaborators, including myself, went to work actually modeling not just clump A, but clumps B and C, and looking at the evolution of those stellar populations. The idea being that maybe the stars that formed in those objects at earlier times actually produced the radiation that would be required to destroy H2 molecules in clump A. And we found, by doing some modeling of that process, and shown here as the H2 dissociation rate against the H minus photodetachment rate, which is important because H minus is an intermediary for the production of H2. We have evolutionary tracks for modeling that are derived from modeling the stellar populations in clumps B and C, and you can see that they all spend some time above this gray region, meaning that the H2 dissociation rate really is high enough potentially to set the stage for direct collapse black hole formation. So what we've done at Los Alamos since then is actually to run radiation hydrodynamic cosmological simulations of the formation of CR7. And what we've done is actually to take a target halo at redshift 6.6, where that object is observed, that we take to be 3 times 10 to the 10 solar masses in the simulation, which is a well-motivated mass scale for that object to be living in. And then we actually start the calculation at a higher redshift by placing a direct collapse black hole in an atomically cooling halo, and we track the accretion onto that black hole as well as the X-ray feedback from that accretion process all the way down to redshift 6.6, and we see can we reproduce sort of the observed emission from that object. And this is a movie showing the density contours of the calculation and the process of accretion, and the black hole is sort of at the center there. So at the end of the calculation at redshift 6.6, you can sort of see the properties of the gas. These are the size of these images is 20 kiloparsec on a side. You're looking at the center of the halo. This is the ionized fraction, density, and temperature profiles. At the center of that box is a black hole that's grown to a mass of about 2 times 10 to the 7 solar masses, and it accretes at an instantaneous rate about a quarter of the Eddington value. And it's actually important to point out that the accretion rate varies fairly rapidly in the calculations. And so just before the snapshot, in fact, the accretion rate is something closer to the Eddington value, and it can fall off on timescales as short as about 1,000 years. Which is important to point out when interpreting sort of what we're finding in terms of the emission and relating it to the instantaneous black hole accretion rate. Which we have done, and we've done a comparison working from, again, that snapshot that I just showed of the nebular emission that we calculate from the cosmological volume and comparing it to the observations of CR7. What we show here are profiles of the Lyman alpha emissivity in the H2 1640 angstrom emissivity, again, that key nebular emission line that's indicating a very hard ionizing spectrum from the source. There are 2 processes that are calculated here, recombination and then also just collisional excitation followed by radiative de-excitation that's caused by the heating of the gas by X-rays. The overall conclusions are down here in this table where we show the Lyman alpha luminosity we obtained from the simulation compared to the observation, as well as the 1640 luminosity and then the widths of those 2 lines. Looking at the Lyman alpha luminosity, you can see we do indeed find something that's quite elevated something like 5 times 10 to the 44 erg per second or so, well above the observational lower limit, and consistent with that. The helium-2 line luminosity is actually very close to what was observed for CR7. The line widths, Lyman alpha line width is actually itself also very close. The helium-2 line width is a bit further off, but still within a factor of 2 or so. The overall conclusion being, I think that qualitatively, you can show in a detailed calculation like this that you can find an object that looks like CR7 in this basic seeding scenario where you have a black hole formed by direct collapse that accretes gas over a couple of hundred megayears, and looks like this at redshift 6.5. So in the last few minutes that I have, I want to turn back now to the population 3 scenario, either for CR7 or other sources that might be observed in the future by James Webb and other telescopes. Of course, the complication with that model is that you have to form population 3 stars extremely quickly in order to ramp up the luminosity and get something as bright as maybe a CR7-like object or anything even close to that, really. So one thing I did a number of years ago in 2010 was actually to think about how you can form population 3 stars at late times and how you can get the cluster of population 3 stars bright enough that it could actually be detected. And the way to go about that really is to suppress star formation and halos until you grow those halos up to as large a masses as possible, and then allow the primordial gas to fall into them and really quickly convert some fraction of the gas into stars. And that seems to be the only hope you have for making the very brightest population 3 starbursts. And this can be achieved in part by Lyman reverter radiation destroying H2 molecules. That suppresses population 3 star formation. And another very powerful way to do that actually is just to invoke the photoionization of the gas. So if you photoheat the gas during the process of reionization, for instance, it becomes very hot in the IgM, 10 to the 4 Kelvin or higher, depending on the ionizing spectrum. And then the gas doesn't collapse into dark matter halos until they've grown to a mass scale of about 1 billion solar masses. So this is way higher than sort of POP3 star formation in many halos. And if this process does happen, then you have something of order 10 to the 8 solar masses in gas that is a reservoir for POP3 star formation. The question is, of course, what fraction of that gas do you actually put into population 3 stars? And that's a question that I think needs requires a lot more research in order to sort of estimate the maximum population 3 stellar mass you might attain. But it is a scenario for obtaining a fairly bright population 3 starburst. So Visbal et al. At Columbia actually quite independently adopted a framework similar to this to try to explain the emission from CR7. And what they did was to look at the ionizing flux that would be required to keep the gas at the distance between clumps B and C ionized at clump A. And what they found was, assuming what they found is required to explain CR7, they also applied in their model to look at the number density of objects like that they would expect. And what I've done is take the number density they find and actually plot it on top of the sort of very rough estimates from 2010, and you'll notice that the natural units here are number of population 3 galaxies per co-moving gigaparsec cube. So these are very rare objects indeed if they do form. The two lines here, up just above and below, the estimates from Visbal et al. Are what I had found in 2010, just sort of surveying a number of dark matter halo masses that might host these objects. And in broad terms, those estimates are in basic agreement. But just to reiterate, I mean, the star formation efficiency to explain CR7 will need to be something like a conversion of 7% of the baryons into stars on a very short time scale. And there are other complications with that model explaining CR7, including the one pointed out by Smith et al. That the velocity line shift between Lyman alpha and helium-2 1640 is quite hard to accommodate in this picture. It's also, of course, true that if there is a definitive detection of metal lines from clump A, that the population 3 scenario also has to deal with explaining that, which is clearly quite difficult. So that brings me to my summary. I think there should be some time for questions. I haven't been cut off yet. So I'll quickly summarize. So the deepest observations of the first galaxies are going to be coming soon. We have at least one object, which is a really nice test case to study and try to understand in CR7. And even if it turns out not to be a primordial object, I think that we've already made some important progress in trying to understand it that we can apply to future objects that are unexpected coming from James Webb and other missions. That object in particular appears to be most likely powered by an accreting black hole that's accreting a very low metallicity gas, if not primordial. And the population 3 scenario sort of struggles to explain that object, but this picture in which you may form the most massive population 3 starbursts during the reionization of the universe, I think may hold some promise in allowing us to find population 3 galaxies with more powerful observations in the future. So I'll stop there.
Great. Questions or comments for Jarrett? Just see. Oh, is that a half hand or is that a real hand? No, that's a half hand. The Chiaki did have a real hand up, yes.
How frequent do you expect this event in terms of cosmic ray? Do you have any estimates for this?
For the CR7 objects?
This kind of,
this kind of thing.
black hole collapse.
I mean, the estimates vary fairly wildly. I know that a number of authors have shown that you can easily, or you may be able to produce enough just to explain the number density of the most massive black holes powering quasars at redshift 6, so on the order of 1 per cubic gigaparsec co-moving, but it could be somewhat higher than that. It's fairly uncertain, really. It's very surprising to actually find something that looks like it might fit the bill already. And I guess I can go back. Well, I suppose these estimates are actually more for the population 3 scenario and don't speak as much to the direct collapse.
Okay, Dan?
Jarrett, I have a quick question for you. Presumably, X-rays from the black hole will trigger star formation in the host halo through secondary ionizations and molecular hydrogen enhancement.
Right.
So, do you get star formation rates in the host halo whose total production of metals is below that observed for the system to date?
Yeah, that's a really good question. I know that I believe John Wise and collaborators have actually found that does seem to happen in the direct collapse scenario, right? You trigger H2 formation due to X-ray feedback, as you said. In our simulation, we didn't see that happening, but we had different star formation prescription, and I think it's something we need to dig into the details to understand better. I also think it depends on the halo itself and its growth history. You need to choose a halo that really is representative of that object. In principle, it can happen. I think it may be a bit difficult to envision having just a little bit of star formation. Once you form some metals, they tend to allow cooling and progressive star formation thereafter. But in principle, I suppose it's possible. I think it's an open question.
Yeah, Raphael?
So I really like very much your latest simulation. And what I wanted to ask you is, I think you have provided convincing evidence that indeed CR7 could be powered by a growing black hole.
Sure.
What it's not clear to me is if you can really rule out the possibility that CR7 is a POP3 remnant that has grown up, because the mass and redshift gives ample space for...
Yeah. I know other people in the room have worked on that particular question more closely than I have. I suppose it can be a possibility. Again, suppressing star formation, especially, and keeping not violating the metallicity requirement, I think might be more difficult if you start with a smaller black hole seed. You may be able to invoke the feedback from a massive black hole seed more easily to suppress star formation. That's one aspect I would think. I don't think it can be ruled out either. But it does look like CR7 may fit the bill in terms of providing the background radiation you need at early times. I mean, if there are other ways to really test test those two scenarios, it would be fantastic.
Okay, great. Let's thank Jarrett again.